Somewhere in our galaxy, filed quietly in a star catalog, sits one so vast that if it stood where our Sun does, its surface would swallow Jupiter and reach almost to Saturn. We call it Stephenson 218. By every model we have, a star this size should not be able to hold itself together. And the strangest thing about it is not how big it is. It is how little we are truly sure of. Take our Sun and grow it until it is 2,150 times wider. That is Stephenson 218. Its radius is about 1.5 billion kilometers, or 930 million miles. Now, lift our Sun out of the middle of the solar system and set this star down in its place. Mercury, Venus, gone. Earth, the ground under your feet, now sits deep inside the star. Mars, gone. The asteroid belt. Jupiter, the giant of our planets, buried inside it. And still the surface keeps reaching outward, until it nearly touches the orbit of Saturn. Here is the honest part. It does not swallow everything. Uranus and Neptune, far out in the cold, would survive, still circling the star that had eaten their inner siblings. So when the title says the whole solar system, hold a little doubt. We will come back to that. To feel a size like this, turn it into motion. A passenger jet takes about 19 years to fly around our Sun without stopping. To circle Stephenson 218 at the same speed, it would need about 1,100 years. You would have had to take off in the Middle Ages to land today. And light, the fastest thing there is, circles our Sun in 14 seconds. Around this star, it needs more than 8 hours. Or shrink our Sun to a ball 1 meter across, a little over 3 feet. On that scale, this star is a ball more than 2 kilometers wide, well over a mile, half an hour's walk just to cross. At some point the mind gives up. This number is not here to be understood. It is here to stand in front of and feel small. Before we go further, wherever you are right now, whatever city, whatever hour of the night, drop it in the comments. There is something grounding about remembering that all of us are picturing this from the same small blue dot. You may have heard this star described another way. 10 billion suns. That number is true, but it traps almost everyone who hears it. It does not mean Stephenson 218 is 10 billion times wider than our Sun. The width is only that 2,150 times. 10 billion is how many sun-sized balls you would need to pack inside it to fill it completely. The two numbers are so far apart because of how space grows. Width climbs in a straight line, but volume climbs by cubing it. Make a ball twice as wide, and it does not hold 2 of the smaller balls. It holds 8. Make it 10 times as wide, and it holds 1,000. So take that width of 2,150, multiply it by itself 3 times over, and you land at very nearly 10 billion. It helps to remember how large our Sun already is. You could line up 109 Earths across its face. The Sun is enormous, and we barely think about it. But this is not a story about the Sun being big. Stephenson 218 is a different order of thing altogether. So picture it this way. Filling this star with 10 billion suns is like filling a stadium with peas. You do not see something 10 billion times taller than a pea. You see a space so vast, it can quietly swallow a countless number of small things. That is why 10 billion lands harder than 2,000. It is not a width you can see. It is an emptiness you can fall into. If your brain just quietly gave up, you are in good company. Comment 10 billion below, so I know it broke yours too. Then stay close, because here is the question almost no video answers. How could we possibly know any of this, for a star we can barely even see? We did not send a ruler to Stephenson 218. We cannot even see it clearly. So, how do we get a number at all? We read two things from its light: how much energy it pours out, its luminosity, and the temperature of its surface, written into the colors of that light. Together, those tell you how much surface a star needs to glow that brightly. And from the surface, you get the radius. It is like guessing the size of a fireplace across a dark room, from the warmth on your face and the color of the coals. But there is a weak link, and it is distance. Stephenson 218 sits about 19,000 light-years away, in a region astronomers call the Zone of Avoidance, a band so thick with gas and dust that it blurs everything behind it. Studying this star is like reading a letter through a wet paper bag, and every small error in the distance is magnified straight into the size. There was even an argument about whether it belonged where we thought. It looked too bright, so some suspected it was a nearer, smaller star that only lined up in the same direction. They settled it by measuring how fast it moves toward or away from us, and checking whether it drifts along with its cluster. It did. But not everyone is convinced, and that crack will matter soon. Today, the heavy lifting is done by Gaia, a European spacecraft that measures the distance to more than 1 billion stars. It does it by watching each one shift by a tiny angle as Earth swings around the Sun, the way your finger jumps when you blink one eye and then the other. And it was Gaia that later forced more than one largest star to be measured all over again. Even the distance to this star's own cluster was once put 3 times too far, then corrected. If you think this video deserves more attention, please click the hype button below. Each hype will help this video get recommended more often. Because measuring giant stars is, more than anything, a story of getting it wrong. Take Betelgeuse, the bright red dot on the shoulder of Orion. Around 650 solar radii. If it replaced our Sun, its surface would reach past the orbit of Mars. Its advantage is that it is close, only about 600 light-years away, so we can measure it cleanly. The farther out you go, the harder everything gets. The clearest lesson is UY Scuti. For years it held the crown at around 1700 solar radii. Then in 2018, Gaia measured its distance and found it much nearer than we thought. Pull a star closer, and it does not need to be so large to look as bright. Its size collapsed to roughly 750 solar radii. One better measurement quietly erased the largest known star in a single release of data. The same happened to VY Canis Majoris, once near 1800 solar radii, later trimmed to about 1400. Notice the pattern. Every correction came from a better instrument, not a new object. We thought we knew the biggest, then looked more carefully. A record in the night sky is temporary by design. And here is good news for the skeptics. The tools are catching up. In November of 2024, the European Southern Observatory captured the first close-up image ever taken of a star in another galaxy. It is WO8G64, a red supergiant around 2,000 times our Sun, in the Large Magellanic Cloud about 160,000 light-years away, wrapping itself in an egg-shaped shell of dust. For the first time, we looked straight into the face of a giant like this, which leads to an uncomfortable question about the star we started with. Is 2,150 solar radii actually true? This is the part the title quietly owes you. That headline number rests on two assumptions that wobble. The first is distance. The star drifts at about 89 kilometers per second, while its cluster moves closer to 109, enough that some treat it as a foreground star, not a cluster member at all. If it is nearer than we think, it is smaller than we think. The second wobble is temperature. Its surface reads about 3,200 degrees, strangely cold, colder than the coldest red supergiant our theories say should exist. When the input looks wrong, the size that comes out has to be held loosely. There is a second warning sign. 2,150 solar radii is larger than what stellar theory says a star should reach, around 1,500. When a measurement climbs past the ceiling, the physics predicts, that is usually a red flag, not a miracle. Several scientists who study it say so plainly. The estimate may be unreliable. It may be too high. You can watch the uncertainty move. The star's brightness was put at 90,000 suns in 2010, then 440,000 in 2012, then 630,000 by 2020. Since the radius is calculated from the brightness, it jumps along with it. This is not sloppy science. It is science being honest about a thing it cannot yet pin down. And that doubt travels with all of them. Even the 2,000 solar radii we gave WOHG64 carries it, because every one of these sizes is calculated from brightness and temperature, never measured against a ruler. So the better question is not whether it is exactly 2,150. It is this. Even at the cautious estimate, it is one of the largest stars we have ever met, and we still have not touched the bottom of how little we know. Please like this video to let me know you share the same thoughts. And please share it with others who are interested in this topic. Don't forget to subscribe to my channel to explore the mysteries of the universe around us. Suppose the number is too high. Suppose it is only 1,500. The strangest thing about this star was never how wide it is. It is what could possibly be holding something this stretched out together. And the honest answer is that almost nothing is. Its outer layers are so loosely bound to the core that the star is leaking itself into space, with some of the heaviest mass loss ever seen in a red supergiant. To make that real, It blows roughly 4 to 5 Earths worth of matter into the dark every single year. And over its whole red supergiant phase, it may shed several entire suns before the end. It is slowly taking itself apart at the edges. That is also why there is no clean place to say the star stops. There is no hard surface, no shoreline, only a gradient, from impossibly thin plasma on the outside, getting slowly denser, down to the burning core, thousands of solar radii within. Its radius is almost a philosophical question, and it is so hard to measure because you are not measuring a ball. You are measuring a cloud with a hot heart. To see why it bleeds like this, there is an idea named after the physicist Arthur Eddington. Every star is a tug of war. Gravity pulls its outer layers in, while the light pouring out of the core pushes them away. There is a brightness at which that push of light very nearly matches gravity, and a cold red giant lives right at that edge. That is why it sheds so fiercely. It is like trying to keep ash on a fire that burns too hot. The heat just keeps lifting it away. So it is not holding together so much as slowly coming undone, handing itself back to the dark, one breath of starlight at a time. And if barely holding together sounds like an exaggeration, look at how little is actually inside it. Something this enormous ought to be staggeringly heavy. All that volume has to be filled with something. But Stephenson 218 weighs only about 12 to 16 times as much as our Sun. That is a lot of material, until you remember it is spread across a volume some 10 billion times larger. Stretch that little mass across that much space, and the thinness becomes almost impossible to believe. Here is a way to feel it. The average density of our Sun is about 1.5 grams per cubic centimeter, roughly the density of water, dense enough that from far away it behaves like a solid. The average density of Stephenson 218 is closer to the air around 100 kilometers up, right at the line where Earth's atmosphere fades and space officially begins. And the outermost layers are thinner still. Sit with that. In theory, you could send a spacecraft straight through the outer shell of the largest star we have ever found and barely feel any resistance. It behaves less like a glowing solid ball and more like a vast, faintly glowing atmosphere with a furnace buried deep at its center. A cloud with a burning heart. A star so nearly empty that you could fall through its outer light and barely know that you had touched it. If a star has no real surface and is half cloud, where would you draw the line between a star and a very hot cloud? Tell me, honestly, where you would put the edge. A star this thin, this loosely held, cannot last. And the way it ends is the most spectacular event the night sky has to offer. Right now, it is fusing heavier and heavier elements in its core. At some point, that core reaches iron, and iron is where the story turns. Fusing iron does not release energy. It swallows it. The outward push vanishes in a fraction of a second. The core caves inward, then rebounds in a shockwave we call a supernova, like pulling the last beam out from under a vast stone dome. Here is the part that worries people, so let us be clear. It is no threat to us. It sits 19,000 light-years away, far enough that the blast can do nothing to Earth, yet close enough that when it happens, this star will blaze across our night sky for weeks. It is not a warning. It is a goodbye we will be able to see. How long until then, no one can say. Somewhere between a few 100,000 and a few million years. And before the end, it may change entirely. Some stars at this stage pull their outer layers in and heat into a yellow hypergiant, and this one may be about to shed its envelope into something stranger still. Its size today may not be the largest it will ever be. To picture the brightness, lean on a closer star. If Betelgeuse, only 600 light-years away, went supernova, it would be bright enough to see in daylight for weeks. Stephenson 218 is around 35 times farther, so it would glow about as bright as the brightest planet in our sky, yet still outshine every single star. When that light finally reaches us, and one day it will, would you want to be alive to watch a single star outshine the entire night sky? Comment yes or no. And then stay for the strangest part of all. How many more giants like this might be hiding in the places we simply cannot look? Because we found this one almost by accident. It had been sitting in a catalog for years as an anomaly, a star too bright to make sense of, set quietly aside while easier targets got the attention. The proof of its size did not come from some grand hunt for the largest star in the galaxy. It came from a team simply trying to work out which stars belong to a cluster. The galaxy, it turns out, is not a catalog we have finished reading. And that zone of avoidance, the dusty band that hides so much of the Milky Way, is not a small gap. The most extreme stars tend to be born in exactly the dense, crowded, hidden regions that are hardest to see into. Our whole inventory of what is out there is built on the places we cannot look. We are counting the giants we can find in front of a curtain we cannot yet pull back. That curtain is lifting, but slowly. It was only in 2024 that we managed our first close look at a single giant star in another galaxy. Each new instrument hands us a few more of them, and in the same breath reminds us how many faces we have never seen. So every time someone draws the upper limit with confidence, the universe quietly sets something down on the far side of that line. Not as a dramatic reveal. Just sitting there in the data, waiting to be looked at properly. We do not know where the true ceiling is, and we are not sure we would even recognize it if we met it. So here is where the truth lands. At its largest estimate, Stephenson 218 is a star whose surface would reach to Saturn, and yet that very number is still in dispute, and that dispute is the most honest thing about it. It teaches us two things at once. The universe is so large that the mind simply surrenders, and at the very same time, we are still learning how to measure the things we thought we already knew. Both are true, and neither cancels the other. A cloud with a burning heart, nearly empty, slowly handing itself back to the dark. And we happen to be alive at the brief moment when we can finally look at it and almost understand what we are seeing. Not the whole of it. Just enough to feel how much is still out of reach. We did not find the edge of what is possible. We found the edge of what we can currently see. And that, quietly, is the more staggering thing of all. If you want to know how Gaia rewrote the night sky, the story of Uy Scuti, and the record that fell is the place to go next. And if you want more of the universe told straight, with the uncertainty left in, subscribe and stay a while.